Okay, in this next video then we're going to go through and talk about the multiple predictors of logistic regression. So we're going to go back to the Donner party, and instead of just having one or two variables, we get up to k variables. And so typical goals is to decide if any predictors affect the response probabilities. There's something akin to the overall left test. Make references about which predictors do and which do not affect the process. Again, that's sort of like our t-test or partial f-test. And make inference about how those predictors affect the response and whether they interact. And again, we're going to have to cut some of this out. So we're just going to take a look at where we set up this probability and said we have k variables, and the probability is 1. That's a success as a function of those x's. So what's the probability you succeed given those inputs of the outputs? And so we talked about this, that instead of having the probability, you look at the odds ratio, where you take the probability of success over probability of failure. For example, if you had a probability of success of 0.75, then the failure would be 0.25. So 0.75 over 0.25 would be 3 to 1. You'd have 3 successes for every 1 failure, and that's akin to 75% probability of success. And then what we do is we take the natural log of this adaptation and we get what's called the logistic curve, which has that kind of S-curve where it's mostly 1 on one half of the graph and mostly 0, and then between there's some probability that goes between the 0 and 1. 0 is y is 0, that's a failure, 1 is a success. And we could take that and take the natural log of the odds ratio and fit a logistic curve. So we take the that natural log of the odds ratio and we get this expression, which is a regression model. And the solution then turns out to be that our probability turns out to be this here, the exponential of that, and then 1 plus the exponential of the logistic curve. So instead of just having one variable, we just have multiple variables. And so we could go ahead and take a look at some counts and kind of affect the graph. And we could actually take a look at the odds ratio. What's the change if we take one predictor variable, and change it from B to A? Well, leaving the other unchanged, and it looks like the odds ratio for X with A in it and the odds ratio for B in it, and all these other exponentials cancel out. The great thing about exponential curve, exponential function, we get the exponential beta I times A minus B. And so that gives us some sort of measurement of how we could express the change if we change our predictors, like change in year or change from male to female or whatever. Okay, so let's go ahead and just do these estimations of the betas. So I'm going to go to Minitab and look at my data. Here is my data, and I'm going to do a regression. I could do multiple regression, and I want to do binary logistic regression. And so I have this here. One of the things I want to make sure is that I'm doing the maximum likelihood ratio test. This case is not going to be as important, but later on when if we were going to do this in a normal class, we would then go ahead and evaluate that. So the status, again, I want to see if I survived or not, and the continuous predictors are going to be age and female. So I go ahead and run this, and it turns out to be that it gives me my equation right here. So the probability of survivor is the exponential of my line over 1 plus the exponential of my line. So I'm just going to go ahead and copy that, maybe as a picture, and put this in to, well, first of all, I need the estimation of my natural log of the odds. And so let's see if I can copy this part right here. I'm going to copy that and put that as my natural log of the odds. It didn't give me too much, but that's going to be my natural log of the odd function is 1.063, negative 0.0782, and then plus 0.1.5 nev and 7 female. So that's the line or the linear model that I would get. But then I would go ahead and then estimate what my probability would be. And the probability would tend out to be the exponential of this curve. So let's see, how should I do that? I'll just, let's just copy everything, copy the whole thing and put this here. And my probability would be the exponential of this plane that I developed. So I'm going to take this part right here and place it for y prime and 1 plus y prime, and see if I can't get rid of other things. Let's see if I can make it look like 1 over something. Yeah, it looks pretty good. And so that will then be my equation. So all I have to do is put in age and female into the expressions, and then I can find out what the curve. So let's estimate the probability of survival of a male my age. So I'm going to lie and say that I'm 60 years old. So I'm going to say that my age equals 60. I'm not going to lie about my gender. My gender is male, so that means X female equals 0. So I'm going to plug this into my calculator. 1.63 minus 0.0782 times 60. And I get negative 3.062. And then I'm going to exponentiate that. And then take my answer and divide that by parentheses 1 plus my answer. And it turns out to be, my probability of survival is 4%. I'm dead. All right, 4.5%. All right, let's try the female of my age that I'm lying about. Age is 60 and female equals 1. So again, I'd have 1.63 minus 0.0782 times 60 plus 1.597. Man, the female adds a year and a half. Well, I don't even know that because I have to figure out the exponential. So that's going to add something to me. That gives me negative 1.465. And now I'm going to exponentiate that. You get 0.23. And so take my answer divided by 1 plus my answer. And I get a probability of 0.188. 0.1877. So man, if I were a female, I'd have an 18.7% chance of survival than before. And we could take a look at that. We talked about this as the odds ratio for a female. The age goes down anywhere between 86% and 100%. Or 80, I'm sorry, it's 86% of the previous value of 99%. Whereas a female will add to my survival chances of 1.12 all the way up to 21.7 times as much of survival if those change for a particular value with the age. All right, and here's sort of my p-values. It looks like all of my regression equations, all these predictors should be included, or slopes should be included. So there's a lot of interesting things you can do here, and I may add a couple more videos looking at those responses. Hey, I'm supposed to read. Hey, there I am. All right. Bye.